We will get started. It's my pleasure to introduce Dr. Walter Bowen, and many of you already know Walter, but we've invited Walter to talk about some of the work that he did related to urea placement. And so he's going to share with us his project and the work that he did and the things he learned, and then we'll have an opportunity for some questions and discussion at the end. So thank you so much.
Great. Well, thank you. I'll get started because there are a lot of slides, and I don't want to move too fast, but what I'm going to talk about is a project that before coming to the University of Florida, I worked 15 years with the International Agricultural Research System. And so before coming here, I was 3 years running a program for IFDC, the International Fertilizer Development Center, out of Asia, working with EFAD funding, that's the International Fund for Agricultural Development, looking at ways of improving nitrogen use efficiency in rice-based systems. And so this urea deplacement was a technology that had been developed over the years that we were actually working more on disseminating more widely in Bangladesh, Cambodia, and Vietnam. I'm going to talk primarily about Bangladesh because that's where we developed the technology and also developed the machinery you'll see that's important for being able to produce the product that allows you to use this technology. I just wanted to point out that, are you familiar with Feed the Future? Yep, okay, so you know it's the U.S. contribution to the global food security effort. And if you looked at their latest progress report, there's actually one of my photos over there, but this was, I don't expect you to be able to read it, but on page 16 of the report is a reference to this technology and the fact that it's being more widely disseminated in Bangladesh. It says in Bangladesh, 2.8 million smallholder farmers. At the time when I left there, we had 550,000. So now it's increased to 2.8 million smallholder farmers adopted improved agronomic technologies. One of these technologies, urea deplacement, increases yields, reduces the cost of fertilizer, and reduces runoff into drinking water and evaporation to the atmosphere. As a result, incremental on-farm sales of rice increased by $30.5 million. Adoption of other improved technologies in Bangladesh increased on-farm sales of fish and shrimp by $10.5 million, and horticulture by $7.8 million. I just want to point out the link that I'm going to go back in history a little bit to some of the data collection we did that actually helped sell this to the Ministry of Agriculture, and which led to their implementing technologies that made the urea deplacement technology more widely disseminated in Bangladesh and also now in Cambodia and Vietnam. So the purpose of this talk will be primarily to tell you a little bit about what we consider as an innovative technology, a very simple technology that decreases the release of nitrogen to the environment or pollution due to overuse of nitrogen, increases the efficiency of urea fertilizer use, which is the primary form of nitrogen fertilizer applied to rice is in the form of urea. And it's being practiced, as I told you, 550,000 farmers, and now that's increased, you saw in the Feed the Future documentation, to 2.8 million farmers. That's the latest estimate. And the work I'm going to be referring to was in the early 2000s, and the series of documents that I prepared after were around 2007. So this has been, since 2007, the government implemented a very big campaign on getting the word out, making more of these machines available as well. And as you see then, that's the reason we've gone from 550,000 farmers to 2.8 million farmers over these past 6 years. So nitrogen, it's an essential element for life and food production. And this is an often quoted statement that came from Wycliffe Smil from a book he did on nitrogen. He's at Saskatchewan University. 40% of the world's population owes its existence to nitrogen fertilizer. That is, if it wasn't for the capability of us to be able to take molecular nitrogen with its triple bond and actually break that into reactive nitrogen, there would not be enough nitrogen on the planet to produce enough of the crops, the protein that we would need for about 40% of our population. So the Haber-Bosch project, if you go back to the early 20th century, there was a lot of concern about running out of nitrogen, therefore running out of food. There just were not, the primary source of nitrogen was recycling, either using nitrogen fixation in legumes, beans and peanuts and peas, etc., or rotating with green manure systems, but there just was not enough land and that's the reason this nitrogen fertilizer has become so important for us to be able to feed the population base that we have today is because there just was not enough naturally created reactive nitrogen to produce the food that we're consuming today. Okay? Just to give you an example of the importance, here's from 1960 to 2005. On the right side, we have the paddy production, 1 million tons, the blue line. And you can see that over time, the country of Bangladesh, it went from a population of around 40 million to over 100, but right now it's around 144 million people. It has a population density of 1,000 inhabitants per square kilometer. It's the most densely populated country. You know, it's not an island state like Singapore or even the Netherlands. It's much more densely populated than even the Netherlands. Well, you can see that paddy production has been able to keep up more or less with population growth. And that's been due in large part to the use of irrigation systems during the cool winter. So the winter, you'll have lots of sun, cooler temperatures, but not freezing temperatures. And so as long as you got the water, there's no rainfall, but as long as you got the water through irrigation, then you're able to produce quite a lot of rice. So they're producing rice year round in the rainy season and the dry season through irrigation. Well, they also have improved germplasm, and then as well the use of fertilizers. So here you can see that the urea consumption was parallel with the increase in paddy production or the rice production. Okay, so we see nitrogen has been critical to, in a specific example of rice, increasing rice productivity and production in Bangladesh. Well, nitrogen is also a pollutant when too much reactive nitrogen is released to the environment. So let's say, perhaps you haven't heard that term before. Has anyone heard the term reactive nitrogen versus non-reactive nitrogen? Okay. Well, reactive nitrogen is basically all biologically, chemically, and radiatively active compounds. The ammonium ions, nitrate, organic nitrogen forms, etc. So that's what the plant takes up. As you know, we have inert, the triple bond into the nitrogen molecule, the N2 molecule, is what, 75% of our atmosphere. But it doesn't react with anything, it's inert. But microorganisms are able to take that nitrogen, as a biological nitrogen fixation process, and able to break that microbiologically into reactive forms of nitrogen that then react with the oxygen or with the hydrogen to produce reactive compounds. Okay? Well, and that's what the Haber-Bosch process does. Through high pressure and temperature, it is able to break that triple bond, and then you have single molecule then of nitrogen, which is able to react with the oxygen and the hydrogen. Well, the concern is so great now about the nitrogen becoming almost a pollutant. It is a pollutant. That there is an international nitrogen initiative, and you cannot stop the use of reactive nitrogen. We need it to produce food. Well, the objective of this group is to minimize the negative impacts of nitrogen on human health and the environment, and then at the same time trying to optimize the beneficial role of nitrogen in sustainable food production. So if you were to go to initrogen.org, you'll see that this is definitely a global effort to try to better understand how we can be more efficient and using nitrogen and minimizing its release to the environment. So excess NR, which would be the reactive nitrogen, is a major contributor to many environmental problems. Global warming, nitrous oxide, along with methane and CO2 are the three principal global warming gases. Nitrous oxide is much more potent in terms of securing the infrared radiation bouncing back off from the Earth. It's much more efficient and it lasts much longer in the atmosphere than CO2 does. Acid deposition, of course you know the acid rain, the problems of basically the hydrogen and nitrate forming nitric acid, acidification of soils and water, eutrophication of coastal waters, the loss of biodiversity because of this change in the nutrient content, stratospheric ozone depletion, and at the same time increasing tropospheric ozone and aerosols, the smog. Well, basically what happens is that once you apply a nitrogen fertilizer like urea, which is 46% nitrogen, reactive nitrogen, when it starts to break down into the ammonia and ammonium ions and then eventually nitrate. Well, the plants will take it up as ammonium or as nitrate. Well, if there's not an actively growing plant there to utilize that ammonium and nitrate at the time that this is a very dynamic chemical process that if a plant is not taking that up, then it can potentially be lost either through volatilization, that's the ammonia, lost to the atmosphere, as nitrous oxide, nitric oxide, or as runoff and leaching, primarily as nitrate. Okay, so if an actively growing plant is there, they will take advantage of this. The problem is this balance we're looking for is being sure that when the plant is actively growing, that the reactive nitrogen, the nitrate and ammonia forms, are there for plant uptake. If they're there and you're forming ammonia and nitrate and there's no actively growing plant, then of course it's going to get lost to the environment by one of these processes. And that's where it becomes primarily a pollutant. You see on the far right, there are, through the denitrification process, eventually some of the reactive nitrogen will be converted back to the triple bond inert nitrogen molecule, the N2 molecule. Okay, well, if you look at nitrogen deposition, and this is primarily when we've had ammonia volatilized, going back up to the atmosphere and then forming nitric acids or nitrous oxides in the atmosphere, then some of that comes back. And you can see in this global representation that the amount over on the far right side is the key. You can see that it's primarily where we have most of our agricultural activities in the highest populations. Well, what is happening is over time, the estimated amount is going to increase much more through industrialization, through continued agricultural development and production, through greater use of automobiles as well. And so, of course, South Asia, where the highest population density is and where so much of the rice production, the rice fields are as well. And some of that can be methane losses from, if you look at cattle, you look at methane, as a global warming gas, it's pretty much in the same parts of the world that the problems with nitrous oxide are, and therefore the nitrogen deposition. What this is actually measuring is that when it comes back to either to water or to land, then you have the eutrophication, and you begin to have the acidification, you have the impact on stratospheric ozone levels as well. So in other words, the darker, the closer it is to the purple, the more polluted the environment is, the air as well as the land and the water. Okay, well, what are the prospects for increasing nitrogen use efficiency? The goal is, of course, we recognize we have to have nitrogen to get, particularly for non-legume crops, to get the production that we need for our food. Well, some of there are various ways of tackling this issue of increasing nitrogen use efficiency. One is genotypes that are more nitrogen efficient. They might have a more ubiquitous rooting system and take up more of this reactive nitrogen in the soil itself. You may have management practices that are more efficient, and this is where the urea deep placement that I'm going to talk a little bit more about comes into play. There's also broadcast according to plant need. The LCC is a leaf color chart that they use a lot in rice-based systems, where the farmers can go out and actually see, based on some correlations that have been done, when it gets to a certain light green color, then you need to apply so much nitrogen fertilizer. And that's at a period when the plant is actively taking up and needing nitrogen, so that's when you would apply it. You don't apply it all at the beginning of the season like you might with phosphorus or potassium, because it will get lost from the system, will be lost before the plant goes through its active uptake phase. Well, then there's also more efficient fertilizers, such as controlled release fertilizers. It's a mechanism whereby the ammonia or the urea may sit there in the soil and become, as the temperature, with time, with the temperature and with moisture, it will begin to release more slowly, that would, in a fashion that matches more appropriately the root uptake or the plant uptake demand for nitrogen. Okay, so we're going to focus on urea deep placement. And so urea deep placement is an alternative application method that increases urea use efficiency in flooded rice. On your left side here, we have the less efficient, which is the predominant form of applying the urea. They might go out and do it 2 or 3 times over the growing season, but they're broadcasting it and they're throwing it on top of the water. These are irrigated rice fields. And so depending on wind conditions and depending on the pH of that water, you can have a good bit, as much as 2/3 of that nitrogen lost to the atmosphere through volatilization as an NH3. Well, the deep placement, it's a little more work, but in systems where you have labor that's actually transplanting on a plant-by-plant basis, you'll see later it is actually less work than doing that. Here, what you're doing is actually putting into the saturated soil a big briquette of urea. And that, because it's in a saturated zone, and we'll look more closely at the reasoning for this, if you take this drawing, assume that this is the saturated soil. You have a very thin layer of aerobic conditions at the interface of the water. This would be the water and then irrigated rice system. And so you will, in this anaerobic zone, when you place the briquette there, that urea remains as ammonia. So the microbes that normally facilitate the process of ammonification cannot work without oxygen, so that it sits there as ammonia. And so over time, the plants then will come and begin to take up that ammonia. Yeah. Now, where there's oxygen in the water, that will then be, you'll have nitrification. The nitrate form of urea is very, it could go back into the water and then eventually be lost through volatilization. Or if it's a leaching environment, if you don't have a well-puddled soil to prevent water passing through the soil profile, you could actually lose some of that nitrate as well. Because the nitrate will flow almost together with the water. Yeah. Okay, so basically what this does then is it puts the nitrogen physically in a saturated zone where there's not enough oxygen for the microbes to convert this ammonia to nitrate. So it will sit there until, in the plant over time, becomes basically a slowly available form of nitrogen for the plant. Okay, what does this super granule product look like? Well, the pre-filled urea, what you saw the farmer broadcasting, is over here up the top left. Well, all you do is just physically compress that urea to form either a super granule as a tablet or as a briquette or as a spherical form. It depends on the type of machinery you have that would actually physically compress this this urea. So there's nothing added in this compression process. There's nothing added to the urea. It's just the urea, the pre-filled urea itself. So it's really, really simple concept and a fairly simple process in terms of making the products. Well, what has allowed this to become a technology that farmers can actually uptake has been the manufacture of these very simple machines that will take the pre-filled urea, and these indented revolving wheels, indented pockets, will just compress that urea and form a briquette. And I have here a video that hopefully it's going to work here so that you can see how simple the process is. So what the farmers are doing in this shed that should be open and have free flow of air, they're putting in the hopper at the top there, they're just putting the pre-filled urea. And that pre-filled urea, the machine which is running off either electricity or a diesel motor, is just making these briquettes that's easy enough then for the farmer to place in the field between plants in that saturated soil zone. Okay. So then you just take this and bag it up and the farmer takes it to the field and applies it. Okay, the product, if it's just a urea briquette, looks sort of like this on the left side. The farmers, particularly the farmers in Vietnam, were interested in putting the phosphorus and the potassium together with the urea. And so you can, if you mix urea with diammonium phosphate and muriate of potash, they do not form any kind of chemical reaction, so you can actually compress those products together and form a briquette. What I see I'm going to be running out of time, so I'm going to go a little bit faster here, and then so that we'll have enough time for some questions. Well, how about its application in the field? All you do is simply place it between every other 4 plants in the field. You place it between the farmer's coming down, he has something that he's carrying his briquettes in, and he's putting a briquette here, and then skipping the plant, place, and putting a briquette there, skipping in between the next 4 plants. Really, really simple. And here is, once again, here's a video just to show you the process. And both these videos were made in Bangladesh with farmers. So you'll see what he's going down. He's being sure that he walks between the plates where he has not put the briquette, because if you step on it and it pops up into the water, then the whole purpose has been negated. Okay? So you can see it is a little bit of work. We've looked at the option of applicators, but the problem is, because this is usually a muddy environment, it's hard to get a reliable applicator that everywhere you try to place it, you can be sure that it's put the nitrogen there. The best way, farmers prefer to do it themselves, because they say, I placed it there, I know it's there, yeah, and I know it's buried, and it doesn't take long. It's a lot less time than the actual transplanting process. So usually when you talk to farmers about, is it too much work? The farmers who are doing it say, no, it's not too much work. The farmers who haven't tried it are the ones saying, oh no, it looks like too much work. But usually when you've got farmers with less than a hectare as their normal for their rice fields, it doesn't take them that much extra time. The kids come home from school and help out, or they hire. Sometimes they hire special help to put that, like they do with the transplant of the rice too. I'm going to make a reference to hundreds of on-farm studies that were done with the rice farmers, and I'm focusing on primarily Bangladesh because we started the studies earlier there. And I'm going to look at a little over 500 on-farm trials, and these were side-by-side plots where the farmer had a chance to use his system the way he normally, if he applied pre-filled urea broadcast, however much he usually did, and then versus the UDP system, the urea deplacement system. The other advantage of precisely placing a measured briquette, one of these briquettes, is that you know exactly how much you put on. You're always putting on the same amount. Yeah. Whereas if you're broadcasting pre-filled urea, farmers, the amount of urea used varies tremendously. It may be what they've learned from an extension agent should be applied, or what they decide they can afford. So, and that's what you'll see in some of the data, that those numbers are really all over the place. So hundreds of on-farm demonstrations comparing UDP and broadcast urea as practiced by farmers. And so those over 500 field trials, side-by-side plot comparisons. We just took, for example, measured differences in grain yield. So what's the UDP grain yield versus the farmer practice? What's the applied nitrogen? How much did he actually apply? How much did we apply in the deplacement? What is the partial factor productivity? That's the PFP. In other words, what is the kilograms of grain produced per kilogram of nitrogen applied? And then an estimate of the profit. What was the profit using the UDP system versus the farmer practice system? Well, what happened was that when you looked at the data, you said these are these two, every point represents those two side-by-side plots. Okay, so this was what we measured in the farmer's practice, his plot. And over here is what we measured in the UDP plot, the urea deplacement. Well, this is a one-to-one line. The closer it is to this line, of course, then the yields were very similar. But what happened? They were almost always higher. The yields were greater. And this is across how many years? 4 different years in both a wet season and dry season. at least 20 different varieties and in different locations around the country. So different soil types, different ways of managing the water, etc. You'll see the almond, which is the blue here, that refers to the wet season rice crop. And the red, which is in the better season for plant growth. If you've got enough water, you tend to get higher yields, and that's the boros season. So what was also incredible was when you took the average to see what the farmers were applying here, it was 134 kilograms of nitrogen per hectare, and here it was less than half, 45% more or less, applying an average of 74. So, of course, all these other variables we talked about, it's pretty clear that your grain yield was greater, on average about a ton more. So you were getting a ton more yield, you were applying much less urea, and so of course your partial factor productivity, or the amount of grain you got per kilogram of nitrogen, was much greater. Okay, so this is just another way of graphing out that same data you saw in the previous curve, just the box plots. All right, well, what about the economic benefits? Well, here, if you look at this labor cost at present rates, so if you take into account that the farmer is actually out there taking a little bit longer for this application, but at the same time, he's doing it it's one-time application. It's shortly after the transplanting season. Okay, it's usually, as you may recall, it was within 1 week, usually after the transplants are put out. So you can see that, according to this box plot, we always got greater profit. Well, then we ran a scenario. What if you developed specialized labor that could do this more efficiently, do this deep placement more quickly, and you might pay them more. So let's suppose we pay them as 3 times more than what a normal laborer gets, which would be an incentive for them to develop the special labor. Well, the farmer still makes a profit. And as you can see, the risk, there's no risk really. It's always coming out on the positive side for the farmer. And if you were to take, this is just another way of looking at averages for the same data. If here the average was 5,200 on the broadcast by the farmers and 6,300, so a little more than a ton more yield, as I said before. Well, then you take into account the amount of fertilizer here. The farmer was putting on 320 kilos of urea. Well, here he's putting on 170 kilos of urea. So much less urea put in the environment, and he's getting greater yield because he's been assured of having the nitrogen there at the time the plant needs it. Yeah. So when you look at these numbers, and when we had workshops with the Ministry of Agriculture, it's like, wow. Yeah, I mean, this is a no-brainer. We know what we have to do. We have to, particularly in this case where they're subsidizing urea fertilizer for the farmers, the country is spending money that it shouldn't be spending on allowing farmers to be wasteful at nitrogen fertilizer use, urea fertilizer use. And they're saying, well, gosh, if we can almost decrease that by half, and the farmers are even going to be better off because they're getting a greater yield, we've got to do this. We've got to follow this dissemination campaign and get the word out. Well, it's not just simply a matter of informing the farmers about this practice. You have to create the market conditions, because this is a specialized product. As you saw, the machine is making the briquette. So you have to develop those machines. So an enterprise has been developed in the country where you have maybe about a half dozen manufacturers of these machines. So there's some competition for prices, so the farmers can get a reasonable price, about $1,000 or $1,200 per machine. Well, what if at the time this scenario was run, we knew that we had 280,000 hectares under the UDP practice. In other words, those 550,000 farmers were farming 280,000 hectares. Well, this is where you look at the scaling up options. Well, across those 280,000 hectares, the amount of urea saved, you're using 42,000 tons less, and you're making this is one season, you're making $12.6 million extra because of that increased yield and the reduced cost of the fertilizer. So this is just one season. Well, when you take this further and look at the area, they have 10 million hectares of rice over those 2 seasons. They're growing 10 million hectares of rice. Well, let's suppose that you just wanted to get as much as a third of that area using this practice, the urea deep placement. Over time, this is what you'll see, that if urea is as much as 300 tons, and it's about $200 a ton, $250 a ton right now. But let's say if you get a third of the area, you're going to be saving in one season $120 million. So you see, in one season, you can pay for a lot of incentive programs, right? Incentives that were developed to get more machines manufactured, to get the word out to the farmers. There are TV programs where they specialized in putting together soap operas on the importance of urea fertilizer using the deep, it's called guti. In the Bangla language, it's called guti, G-U-T-I. So you hear people talking about guti urea all the time, particularly if you go out and talk with farmers. Guti, everyone knows what guti urea is. It's the briquette. Okay, well this, and I'm coming to an end here. This was just to point out that there is a value chain behind this product. And so you have the urea source. They manufacture much of their urea because they have access to natural gas. They manufacture a good bit of their urea in country. But because they have been subsidizing because of the wasteful use of it, it's only about half of what is actually used. Well, when you do the calculations, if they can cut by half the consumption, that means they're producing in country what they need for urea fertilizer. Well, so here you have the machine manufacturer, where price, capacity, quality, product, especially product marketing, et cetera, come into effect. And then the briquette producer. And this briquette producer, like you saw in the film, the video, he could be selling directly to the farmer, or he could be selling to a retailer out in these villages who sell it to the farmers. What often happens is that a farmer buys from a retailer the pre-filled urea and goes to the specialty shop and pays him, say, we did the calculations, it adds 1 cent to the cost, 1 cent per kilo to the cost of the urea. Okay, so here you're paying a little bit more for the urea, okay, but you're buying almost 2/3 less. Well, you're buying 45% less. Yeah. So it's one of those rare, and I think this is why it was highlighted in the Feed the Future report. It's just one of those rare technologies that so obvious. You have to. It has, particularly because rice has grown over such large areas, and because of the importance of nitrogen fertilizer, urea, for fertilizing rice. It's a practice I think over time we're going to see more and more farmers taking up, and it may be eventually a system where the producers of the nitrogen fertilizer, instead of making the pre-filled urea, will actually produce the briquettes and sell it in bulk. Yeah. Of course, then the problem with that is that they cut out all these village producers who have bought these special machines to do it for the farmers. Well, this was the farmers. I just wanted to point out that there are cases where women have actually bought. This woman had a little shop there that she bought. This was one of the first machines for producing the briquettes. This guy is a real hero. The guy in the middle there, touching the machine, he's the engineer who really perfected these machines. Yeah. And these machines, by the way, are being sold. We bought them for projects now in Ecuador and in Haiti. And we bought them from Bangladesh. In the case of Cambodia and Vietnam, we bought a couple of machines that were then reverse engineered by machine manufacturers in Vietnam and Cambodia. So now they're producing the machines there. Okay, so this was just for example, the dissemination campaign in Vietnam and Cambodia, where you had gains being created. Here they would go to homes, and they would say this would be in terms of training, so putting leaves out to be like the rice plants and talking about how it was where you actually placed the urea. Here, this was a race. In this part of Vietnam, they would actually broadcast, it was direct seeded rice. Okay, well then you ask the question, well, how do you do the deep placement direct seeded rice? Well, they came up with their own system. What they did was they would create, I don't know if you can see little grids here, they would have the field ready, and before they actually threw out the pre-germinated seed, because they weren't transplanting, they were throwing out seed to start growing the rice, They would come in, and then where those grids cross, it's 25 centimeters by 25 centimeters, is where they would put the urea. Okay, in this case, they would put the fertilizer briquette, the one that had the nitrogen, phosphorus, and potassium. And then they would have games as part of their dissemination campaign, which our project was helping to finance, that they would have these races to see who could be most accurate, because if you placed and it wasn't properly buried, then that would count against you. So you couldn't just go fast and ignore the placement process itself. So something, once again, it's almost too simple. Here was you can see by the darker color, this is where they're producing in Vietnam the fertilizer briquette, the one with the nitrogen, phosphorus, potassium, and then the machine over on the right side in Cambodia. And participatory on-farm testing. So this is how that data I referred to earlier would come from working together with the farmers to actually measure in the respective plots the yields. And then in conclusion, this here was, at that time, this was the Minister of Agriculture. So here he was out in one of the Guta urea sites, and they were doing a news program on it. And so it's become this guy here, the one that's up at the top there in the middle, he's a very famous TV personality who does these special news programs. So once we got him on board, it took off like wildfire. Everybody, he came out to visit once. He said, "Oh wow, this is neat stuff." He was talking. You could just talk to farmers, and you could see the farmers. There was nothing. There were no complaints for them. The only complaint was there's not enough product. I can't buy it over here on my farm because I have to go too far to get the briquettes made. Well, so here the UDP technology should be made more available to farmers to increase the effectiveness and efficiency of urea fertilizer and to reduce the release of nitrogen to the environment. Okay, that's it. So we do have a few minutes. Yeah.
Let's thank Walter first.
Yeah, yes.
What kind of health impacts do does working directly with nitrogen, the little piece of nitrogen for those into the gas have for the farmers?
You're talking about, well, the farmers themselves, no, it's the same thing whether they're broadcasting it by hand or just taking the briquettes, the same thing. And there's no problem using it, getting it on your skin. The problem is if you're in a closed environment and you're crushing up all that urea, you get ammonia release, you can smell it. And so we tell them you have to do it in a well-ventilated area, and it's best to use the mask. Of course, you didn't see any of the guys using masks there. But it's not deadly, and it's as long as you've got a little bit of wind coming through, it's not as bad as a chicken house, for example. Yeah.
I understand that due to the unique growing nature of rice, that this has been possible. Is it possible to change the structure formulation at all of urea to apply this to other cereal crops, wheat or?
Yes, that question naturally came up. Like, if this works so well for rice, what about for upland crops? Well, remember in rice, the reason it works is because you have a saturated zone. So you're able to put that briquette into an area where there's no nitrogen, where there's no oxygen. And so we know it's going to remain there as either urea or ammonia. Over time, it will go from urea to ammonia, but the ammonia is not going to go anywhere. It's going to stay there in the soil till the plant root comes to it. Well, if you put it in an upland soil, let's say, for example, maize, right? And let's say if it's a Florida soil, sandy. Well, what's going to happen is that there's no way you're going to keep oxygen out of there. You have to have oxygen for the plant roots of the maize or the corn to grow properly. Well, what will happen is that briquette eventually will convert all to nitrate. And then when water comes through the profile, you could have leaching losses. Yeah. But what we did find, at least in upland soils that have more clay, just by the fact that you're putting this briquette, which is a very concentrated form of the ammonia, just that, the fact that it exists, even though it is an environment with oxygen, because it's so highly concentrated and so big, what happens is that the microbes take longer because it's actually deadly to them if it's too much ammonia, right? So it takes longer for them to come in from the sides to start chipping away at it, to start converting it from the ammonia to nitrate. Yeah. So what we have seen is you actually do measure it becomes more slowly available over time rather than just putting the pre-ed urea out. Yeah. And we did find too with vegetable crops particularly, you could target precise amounts on a plant-by-plant basis. And we have farmers who are rice growers who became exposed to urea through their rice production system, and so they use it for their banana crop, for their vegetable crops, for their sugarcane crops. You can find it being used that way. And there is some, depending on the soil type and the amount of rain or water that goes through the soil, you could see benefits. Yeah. Uh-huh.
You mentioned that access to protect producers is the limiting factor, or at least that's been identified as the leading limiting factor.
Right.
To what extent is the accessibility of one of those producers dependent upon what kind of community you live in? Because presumably somebody has to be able to purchase the equipment to become a protect producer.
Right.
So are there disadvantaged areas where nobody can afford to buy that equipment, so they don't have the possibility of having access to it?
Yeah. Well, what we found, and I'll take a little while to get a more direct answer to your question, but what we found in some cases where we'd taken the product out and worked with farmers, and then if we left and we came back later, we found out that they weren't using it any longer. Well, you asked them why, and they said, there's no producer. There's no machine anywhere nearby. So it should have been rather obvious to anyone who's working on this. Well, the reason there's no machine is, as you said, perhaps no one had that $1,200 to invest. Well, what the government's doing now is it's providing incentives. So, for example, a partial loan or a complete loan. As word has gotten out, more and more entrepreneurs or businessmen or businesswomen, like the one woman you saw there, have actually decided to buy it, and they sell. They sell use of the machine to the farmers. So over time, they recover their cost, and then they begin to make money. Yeah. So if someone can come up with that initial investment, either through an incentive program they've been helped by the government policy, or else they just have enough money themselves, then over time they can begin to recover that investment and make money. Yeah. So it's become like a cottage industry, particularly in Bangladesh, where it's more widely practiced.